Yes, sir.
Okay, so yesterday we showed the existence of eigenvalues. So if you are not asking questions, please mute yourself. Otherwise, it's difficult for me to change the screens and go there to mute.
Sir.
Yes.
सर कल जो हमने थ्योरम पढ़ी थी ना, मतलब कि अप्रोक्सीमेशन थ्योरम, मतलब लेंथ ऑफ consecutive zeros and the number of zero मतलब vanishes point, तो जो number of points there vanish the yt, वो उसको थोड़ा सा elaborate कर दीजिए। वो जो summation जो आपने लिया था, मतलब t के मतलब k equals to 0 to m tk minus tk minus 1 equals to b minus a, ये put कैसे करा वो समझ नहीं आया।
So this is the AB and these are the zeros of right. So if these are the zeros, how many zeros are there? 1, 2, and 3, right? So look at the length of subintervals of these zeros. One is this t2 minus t1. The next t2 minus 1 is this, and the next is this and this. So the sum of these intervals is going to be AB, length of the interval AB, right?
Yes, sir.
That's what I wrote. And each of this t2 minus t1, okay, is less than pi by say lambda m. Therefore, each of these, right, there are n such things are there. Therefore, the n such things are going to be less than n pi by this, right? For each between any two consecutive zeros, right, is less than this. Therefore, n such consecutive zeros are going to be n pi by lambda.
N pi upon lambda n.
Yeah, so that's what he said.
Okay, clear.
So, you have any other questions from the previous lecture?
सब 4-5 दिन पुराना है, मतलब वो फेस प्लेन मेथड का क्लियर नहीं हो रहा था।
फेस प्लेन मेथड,
यस सर।
व्हाट इज नॉट क्लियर देयर?
सर एक्चुअली हम ड्रॉ नहीं कर पा रहे हैं, मतलब जैसे कि आपने ड्रॉ करा है ना, इम्प्रॉपर नोड, प्रॉपर नोड, शेडल पॉइंट, तो इफ अगर हमें कोई सिस्टम गिवन है और हम उसका सॉल्यूशन निकालते हैं, देन आफ्टर हम कैसे उसको ड्रॉ करेंगे?
You take one particular solution, take for some C1 and C2. Okay, say C1 equals to 0 and C2 equals to 1, or C1 equals to 1 and C2 equals to 1. It becomes a function. You draw that picture of that.
सर जो पर्टिकुलर एग्जाम आपने दिए थे ना, उसी को एक बार बता दीजिए कि ये ड्रॉ कैसे किए गए थे।
It is you have the functions x1. I said these are the functions x1 and x2, right? This is x1 and this is x2. So look at what is how the x1 looks like and x2 looks like. These are the two linearly independent solutions, right? So depending on C1 equals to 0 and C2 equals to 0, you get the how these things look like on the phase plane diagram. It only says that you know, the direction how these things look like. Maybe okay, I will take some other class because I have to project that one now to see those examples. So any other things from the previous lecture or on the boundary value problems?
Yes sir. Sir, one more thing, जो questions आपने मतलब ये फेस प्लेन मेथड के दे रखे ना, फाइंड द स्टेबिलिटी, तो उसमें जब rx मतलब क्वाड्रेटिक फॉर्म में है, मतलब जो fx अपन मतलब नॉन होमोजेनियस सिस्टम में, तो वहां पे हम सॉल्यूशन उसको f मतलब x प्राइम इक्वल्स टू x इक्वल प्लस fx बना के कर सकते हैं, मतलब कि अगर सिर्फ अपन लीनियर पार्ट के आइगन वैल्यूज देख लें।
Yes, of course, we can always do that.
Okay, sir.
You can always do that. The only thing is that when you go to non-autonomous systems, the eigenvalues characterization doesn't work. That's where you see the importance of Lyapunov functions. Okay. So what we did so far is that we found there is a sequence of eigenvalues for a Sturm Liouville problem. So you should remember what I'm saying. The Sturm Liouville problem is p x prime whole prime plus lambda q to x equals to 0. Okay, in an interval AB, and you have one boundary condition B1, okay, of consisting of B1 of x at the points at the point A equals to 0, and other one is the point B 0. So this B1, I should say that it is x comma x prime. Okay, it's a linear function in x and x prime. It's a linear function in x and x prime. So something like C1x plus C2x prime. Okay, so these are linear. Linear in x and x prime. So there are two boundary conditions that are given, and you have the remember that P is strictly positive in the closed interval AB, and P is a C1 function in the interval AB with the derivatives continuous up to the boundary. Okay, so the derivatives up to the continuous up to the boundary, you can write P prime belongs to the C of the closed interval AB. That is the condition. And Q is a continuous function, okay, in the closed interval AB. So these are the conditions for the Sturm Liouville problem. And this AB is bounded interval. Bounded.
Sir, you are not audible.
Sir, your screen is paused.
Okay. So now my screen, can you see that, or should I share again? Let me share once again.
Yes, sir.
Is that fine? Now can you see my screen?
Yes, sir.
Okay. So such problems are called Sturm Liouville eigenvalue problems. So I already said how to transform this problem into the problem that we studied earlier, that is x double prime plus q into x. Okay. Once if you have these things, then you can take x equals to exponential of p into y. Then y satisfies a nice equation which is in the form of y double prime plus something times y equals to 0. Okay, so these problems are similar. Okay, so I mean to say if one of them has solution, the other one also has a solution. So the eigenvalues satisfy the, if suppose lambda and phi is an eigenpair. Suppose this is an eigenpair, then it satisfies the following relation. Just I'm multiplying this equation with this eigenfunction. Okay. No. Yeah, it satisfies this one, a p of t into p prime square is equals to lambda times the integral q into p square. Okay. So this is this implies what my lambda is. Okay. So lambda becomes the integral of p into p prime square upon integral q into p square. So this is if you see that what we showed is that there is a sequence of eigenvalues with the, and we also showed that lambda is going to be a positive eigenvalue if q is positive. Okay, so if q is positive, then lambda is also positive. All eigenvalues are going to be positive. Therefore, there is the smallest eigenvalue. Right, so that is going to be lambda 1, which is positive eigenvalue. So if you see this, what this fellow is here, this resembles something like in case of matrices, the product AXX, and this is XX. Say in case of Q equals to 1. Okay. In case of Q equals to 1, this is something like the product AXX upon x comma x. So this is what you would have seen while studying the matrices, the how you characterize the eigenvalues. So if lambda 1 is the smallest such number, then what is that going to happen is that this is phi. So this lambda 1 is going to be less than or equals to the integral of p into u prime square upon integral of q into u square for all u, which are C1 functions. So this is a very important inequality, okay, which is known as Poincare inequality. So this is a very important inequality in analysis, and the proof of this inequality in case of real line, case of and it is true only in the bounded domains. It is not going to be true in case of unbounded domains. And the proof is actually comes from the these eigenvalues. Okay. The smallest eigenvalue, which is positive. Okay. Okay. So this is one consequence of this, and a theorem which I am not going to prove here is says about the question that I raised. If you have the eigenvalues and eigenfunctions, how that going to help us to get the solution in the form of eigen expansion. Okay, so this is suppose lambda I is a sequence of eigenvalues such that this lambda I goes to infinity and and these phi i's are eigenfunctions. Okay, phi i's are eigenfunctions. then the following happens. Any continuous function on AB with f at A equals to f at B equals to 0 can be written as where the ck or the integral of f to vk on integral of vk square. So this is known as the Fourier series. This is known as the Fourier series. This is known as the Fourier series. So you can do this for all the cases where you have the sequence of eigenvalues and sequence of eigenfunctions. But the sequence is to be an unbounded sequence, of eigenvalues. Okay, so unbounded sequence of eigenvalues, and the eigenfunctions pi. So we have already shown that the sequence, the eigenfunctions corresponding to distinct eigenvalues is going to be linearly independent. Okay. And therefore, you can apply the Gram-Schmidt orthogonalization process to actually orthonormalize them. Okay, you can actually orthogonalize them, and normalization in a way just it's a simple thing. And what more importantly is that any continuous function, okay, can be written in this form of a series. And the series, what's the meaning of writing in the series? The series converges. Once if I write the series should converge, okay, in the metric d of fg, okay, is equals to integral a to b mod f minus g square power half. I don't know if you have seen this kind of a metric on the set of continuous functions. Okay. On the set of continuous functions, this becomes now a metric space. So in this metric, the series is going to converge. The series is going to converge. Okay, so that is the we will use this fact for writing the solutions. Since every continuous function can be written in this form, we can. So what is basically the method of eigenfunctions? I'll tell you the method, and or I can do an example and then do the method. First, let us do an example. So method of eigenfunctions. So method of eigenfunction, I'm calling it in this particular case, but this is a very general method, okay. And a special case of this is the Fourier series method. A special case of this is the Fourier series method. Okay, so the problem is look at u double prime equals to t with u at 0 equals to u at 1 is 0. So this is a boundary value problem. So how do we solve this? So we look at first step is to look at the eigenvalue problem. Okay, with the same conditions, u0 equals to u1 equals to 0. Okay, so it has eigenvalues lambda n equals to n square pi square, and eigenfunctions are sin n pi t. These are the eigenfunctions. So now we know the eigenvalues and eigenfunctions. So what is basically eigenvalue problem is doing that? It is transforming the derivatives into scalar multiplication. Okay, u double prime becomes lambda u. Okay, so now assume the solution. So the next step is that assume that the solution is in this form. Ut is in the form of ck into sin n pi t. We know that once if I write, if I expect this to be any continuous function, because that has to be true because u is going to be twice differentiable function, which is actually a continuous function. Therefore, I can expect that ut to be in the form of an infinite series like this. Okay. And now in the you have the right hand side also. The right hand side also you can write in the same way. Okay. Also the right hand side t also you can write in the form of, say, fk into sin n pi t. Okay, k equals to 1 to infinity. So if whoever wants a proof of this theorem, okay, you can go to my web page and see that there is a lecture notes for the partial differential equations. You see that the Fourier series methods, okay, the Fourier series methods. So there you will find a proof of this using some concepts from functional analysis. Okay. So proof requires a little more things. Refer to my web page. Fourier methods. Okay. Right. So if you write this, then I can write what these fk's are. Fk's are going to be the integral t into sin n sin kt sin k pi t on integral sin square k pi t. So you can integrate these two things, and then you can find these coefficients are going to be 2 into minus 1 power n plus 1 by n pi. You can do this calculation. Okay, so now since I am writing this ux ut as the sum of ck into sin k pi t. Now I have to substitute in the equation. I have to write what is u prime t. Okay, or I should write what is u double prime t. So when I write u prime t, since it is an infinite series, I don't know whether I can differentiate an infinite series like this. Infinite power series, we have seen how we can differentiate. We just divide it. Okay. So we don't do this directly by term differentiation. What we do is that assume that u double prime also has a Fourier series, because that is also a continuous function. Okay. 1 to infinity dk into sin k pi t. Now I will find the relation between dk and ck. Okay, be the Fourier expansion. Then what is dk? dk is going to be the integral 0 to 1 of u double prime into sin k pi t upon integral 0 to 1 sin square k pi t. Okay, so let me write that. So the dk is going to be 1 upon integral sin square k pi t, which is basically a constant, times the integral 0 to 1 of u double prime to sine k pi t. Okay, now here I apply the integration by parts. Okay, so here I apply the integration by parts. So this fellow will remain as it is, and here this is going to be now take this as u, and this is the derivative of v. So this is going to be sine k pi t du prime at 0, 1, okay, minus the integral u into sine the derivative of this. So that is going to be cos. It's going to be cos into k pi. And you see that this sine is going to be 0 at both end points. Therefore, this constant will remain, and this becomes simply 0 minus k pi to 0 to 1 to u prime to cos k pi t. Apply again the integration by parts. Again apply the integration by parts. So this is constant minus k pi, okay, and this is going to be now cos k pi t into u into cos k pi t at 0, 1 minus the integral, okay, u into derivative of cos again is going to be sine. So sine k pi t into k into pi. So what do I get? This is going to be minus k square pi square, because again u is going to be 0 at 0 and 1. Therefore, the boundary term is again 0. So minus k square pi square into 0 to 1 u into sine k pi t. Okay, so this constant is here as it is. So this is nothing but minus k square pi square into ck. So what are these decays? The decay here is going to be, okay, minus k square pi square into ck. Suppose that is same as differentiating this equation twice. Differentiating this twice, but we are not differentiating the term by term. Okay, therefore u double prime is equals to minus k square pi square into sine k pi t into ck. Therefore, now we can substitute in the equation. Okay, so when we substitute this in the equation, we have the u double prime equals to t implies minus of sum k square pi square into ck minus we have the fk, or you write this is equals to the sum, okay, 2 into minus 1 power k plus 1 by k pi to yeah, both sides there is a sign also, sign. So this implies now what the ck's are, right? So therefore k square pi square into ck is going to be 2 into minus 1 power k by k pi. Okay, so this implies ck is 2 into minus 1 power k by k cube into pi square. So this is the constants are found. So once if I find the constants, I can write what the u is. So you write what is ux. Ux is going to be simply the 2 into minus 1 power k by k cube pi square into sine k pi t. Now you see that the series is going to converge uniformly. Okay, converge uniformly. So there's no problem for the convergence of this. Okay, why is that? Just write the coefficients here. Okay, they're all going to be less than the series. Okay, so all are going to be less than. So if you write this mod of this ck into sine k pi t, it's going to be less than the series 2 by k cube to pi square. So it's, this is a sequence series which converges absolutely. Okay, so therefore the series converges absolutely and uniformly because this series doesn't have any variable t. Okay, so the function this defines now a well-defined, very nice continuous function. Okay, because it converges uniformly and okay, and since yeah, so is the method clear? So this is known as the Fourier series method. This is known as the Fourier series method. So what do we have? So if you take any, so what is the method? The method is the following. So the boundary value problem is for any differential equation equals to f with the boundary conditions b1 at point A is 0 and b2 at A is 0. Okay, so these are the two linear boundary conditions. Then what is the, how do we solve it? The first step is to write the eigenvalue problem. Okay, so first step is to write the eigenvalue problem. You write the eigenvalue problem, that is Lu equals to 0, Lu equals to lambda u. Okay, with the same boundary conditions. The same boundary conditions. Okay, find the eigenfunctions, find lambda n and phi n. Then these eigenfunctions now form kind of a basis. I don't want to call it as a basis in the normal sense, but these are called the Schroeder basis, which you will see in the higher level mathematics. So these are in some sense form a basis for the set of continuous functions, and therefore you can write the f. This is the step 2. You write f in the form of fk into phi k and assume that u is in the form of ck to phi k. Right, so once if u is in the form of ck into phi k, so we have seen how to use the integration by parts. Okay, or one can show that actually this series is differentiable. This actually becomes the ck into L phi k. Okay, so that is basically the term by term differentiation. So this becomes ck into now lambda k phi k. Okay, so this is equals to f. That is, this is equals to fk into phi k. Okay, therefore ck lambda k equals to fk. So this implies this is the relation which we have got for the matrices. If you see the initially itself, the first lecture what I said for the matrices, this is exactly what the matrices is. So if ck is if lambda k is non-zero for all k, then ck is uniquely determined. Okay, so if lambda k is non-zero for any k, then ck is fk by lambda k. In this case, we have unique solution. In fact, yeah, if it is lambda k is equals to 0, then Solution exists only if fk is 0. What is fk? Okay, so if lambda k equals to 0, solution exists if fk is 0. So what is fk? This is nothing but integral of f into phi k is 0. So how many such phi k's are there? So for all phi k, not for all k, for such that particular k. Okay, so if k is 0, so let me say Pm is 0. Okay, if m is 0, then okay, Fm is that this is 0. That means F is orthogonal to Pm. What is Pm? Pm is a solution of Pm is, so Pm is
Eigenfunction corresponding to lambda.
eigenfunction corresponding to lambda m. Okay, solution of L Pm equals to lambda m Pm, that is 0, because lambda m is 0. Okay, so L Pm is 0. So for all Pm belongs to the set where L Pm is 0. Okay, so this is the condition we have seen earlier also. So whatever we thought about the matrices, that is happening in case of linear differential operators also. So this is the same thing one can prove for the linear integral equations, because we have seen that there is a nice relation between integral equations and differential equations already while doing the Picard iterations. Okay, and also a proof of Picard iterations I said by the fixed point theorem. So the same thing is going to happen. So this is actually known as the Fredholm theory of linear operators. See, now what we see here is a simple differential equation coming from the Sturm-Liouville problems. Now we could see that which satisfies that is a matrix, and also you have now a linear differential operator. Now linear differential operator is, you see, in some sense is you can write that as integral operator, right? So you have a linear integral operators also, one can have the similar theory. Okay, and what next is operators. Those operators are called Fredholm operators. So that leads you to study the subject called operator theory. Okay, so let me stop with the generalizations here. And not only these eigenvalue problems, you can even solve variety of eigenvalue problems with what I said. For example, this I'm giving this as in the notes. You can see that the calculations are simple. So equals to 1 in 0, 1. Okay, with the boundary conditions as u at 0 equals to 0 and u prime at 1 is 0. Now you see that this depends on the derivative of u. Okay, so similarly here what you will do is that you write the u double prime plus lambda u equals to 0, the eigenvalue problem. Either you write plus u or lambda u or minus lambda u, doesn't change anything. So u prime at 1 is 0. Okay, so you can find here the eigenvalues again. Lambda m equals to 2n minus 1 whole square by 4 into pi. Okay, and the phi-n's are going to be sine 2n minus 1 by 2 into pi t. So once if you have this, the method is already there, so you can find what are the coefficients. Okay, so you can write the solution u as ck into vk, and then you can find the solutions. You can find ck's. Okay, so this is the method of eigenfunctions. So do you have any questions? The problems is easy here, but you ask the more mathematical questions, that becomes more require more and more analysis or higher level of mathematics. So solving the problems is very easy. Just write the series and then keep differentiating and then substituting and then take the values. Equate to the coefficients and then you get an values. If you have no questions, I will just take few minutes to tell you about some things about the relaxations that you can do on the Sturm-Liouville problems. Yeah. Any questions?
Sir, in the proof of theorem. Sir, actually we have pi square k square pi square ck equals to 2 minus 1 to the power k upon k pi. ओके, तो यहाँ से ck की जब वैल्यू आएगी तो नीचे पाई क्यूब भी आएगा ना, मतलब
पाई क्यूब नहीं आएगा शायद, ओनली वन.
So वही समझ में
pi
आया,
is not becoming cube, right? There is one k which is coming there, right? So that's why you get. There is one. This is coming as k. There is one k here, right? Pi cube also will get, yeah.
Yes, sir.
Just a substitution. So if you remember in the beginning of the class, I said about the Sturm-Liouville problems, which are, what are the type of Sturm-Liouville problems where we showed the existence of eigenvalues. So you see by now that solving a boundary value problem is equivalent to finding boundary value problem of a linear differential equation is equivalent to finding the eigenvalues and eigenfunctions. Okay, the sequence of eigenvalues and eigenfunctions. Right. So the sequence of eigenvalues and eigenfunctions we proved for the Sturm-Liouville problems of this type. So these are called the regular Sturm-Liouville problems. Okay. So the one would ask the question here, the way you should have some good connections with the things about how one can connect the mathematics with the different concepts. You can see some names like regular, singular. These things are proper, improper. These are all related things. If you see that in case of Riemann integration, so in the Riemann integration, we say that Riemann integration is actually defined on closed boundary intervals, and for the functions which are bounded functions. So little later we study this Riemann integration for unbounded intervals from 0 to infinity and for the functions which are not bounded functions. So that we call it as improper. So that means if the function can be a singular function or the interval can be an unbounded interval. So similarly here, the conditions that q belongs to the continuous function and p is positive, okay, and p is a C1. So can we relax all these conditions along with this the interval being the bounded interval? Okay, and we call all these problems are singular Sturm-Liouville problems. Okay, so these are singular Sturm-Liouville problems. So what is the way one could study these problems? Of course, naturally the way that we use the oscillation theory, it's not possible. Right? In the oscillation theory, we assume that P is positive, Q is positive, and Q is not positive, P is positive. Then only we can convert the problem into a standard problem, and then we had the Sturm's oscillation theorems, okay, which require that the equation in the standard form, that is in the form of x double prime plus p into x equals to 0. Okay, so the singular eigenvalue problems. So what are the singular eigenvalue problems? It is we may have unbounded interval, okay, unbounded interval, or the p is not positive. Means that p can be 0. Okay, p can be 0, like you have p can be t square, like you see in the Frobenius method, you have t square into x double prime. So p can be of that type. Okay. So what happens in this case is one can expect the following. The first case is in case of P is okay, so in case of so let me write a general problem that one can look at. So that one can look at a problem of this type. Minus of P into y prime whole prime plus qy equals to lambda w into y. And we have the boundary conditions b1 of a equals to 0 and b2 is 0. Okay, so what is this thing is that if P into W, this is the P and this is W. So it can be that W can be 1 also. So if P into W at the point A is 0, okay, then we can draw this condition. We can draw the condition of P1 at A is 0. Okay, so this we can still find the eigenvalues without this P1 A is 0. Similarly, if PW at B is 0, then you can drop the other condition B2 at B is 0. And both these conditions can be dropped if the interval is unbounded. So these are the Sturm-Liouville singular eigenvalue problems. So what is the idea of, I'm not going to the theory of this, I just blabbering something so that you get some idea when you study the higher level mathematics. So what we had is you can write, I said earlier that lambda can be written as the integral of P into y prime and say phi prime. So, okay. So what we do is so we can write lambda w into y is p y prime whole prime plus qy. This is what we wrote, right? So when I multiply this by y, okay, so then I get lambda into wy square equals to py prime into y, and then you integrate. So here what we will do is the first term will remain, this term will remain as it is, qy square, and this term you apply the integration by parts to get py prime square. Okay, so this is what we apply the integration by parts. Therefore, I get lambda as integral p y prime square plus q into y square on integral wy square. So this is what I get lambda. So if I can show that there is a function, okay, there is a non-trivial function which satisfies this relation, then we call that as an eigenvalue. Okay, so that is the whole idea. So I have to basically find the functions for which this right hand side is achieved. Okay, so the right hand side, or you can call this as I mentioned earlier, lambda 1, the smallest eigenvalue is the minimum over all these things. So you can write similarly the lambda 1, which is going to be the minimum for the set of continuous functions of p into y prime square plus qy square on integral wy square. Okay. So if this is achieved, then lambda 1 is the eigenvalue. So this is a problem. If you see that this is something like the Lagrange multiplier, right? So if you see in the case of matrices, this is going to look like ax comma x by x comma x. Okay, so this is a Lagrange multiplier. So the top one is also a polynomial, and the second one, bottom one, is also a polynomial. So minimizing over a polynomial over another polynomial is the Lagrange multiplier we study in the basic calculus. Okay. So once if I find what the eigenvalue lambda 1 is, I find what is the eigenspace. Okay, so we find what is the eigenspace, call this as say P1, which is E1. Okay, and then you remove this linear combinations of this eigenspace from the set of continuous functions C minus C1. So you can call it as maybe H. And now you do the same minimum over H of the same Py prime square plus Qy square. Okay. And if this is achieved, that is going to be your second eigenvalue. So, and this process you can continue because then this lambda 2 is going to be definitely greater than lambda 1 because you already removed the functions where this lambda 1 is achieved. Okay, therefore, and this theory continues like this, and you will see this kind of these things here are coming from the simple ideas of Lagrange multiplier theory, and we can even do these things for general compact self-adjoint operators in the operator theory that you will study in functional analysis. Then the methods basically go through the same philosophy. But basically these methods are simple to see in case of differential equations. And okay, I'll stop it here. If you have any questions, you can ask me. Okay.
Sir, your web page link, please share in the WhatsApp group.
Yes, yes. What is that?
Your web page link.
My web page go to my web page. No, go to the department and then go look at my name. Click there. You will go to my web page. There it is. It will be written calculus lecture notes for calculus and partial differential equations. So you see in the partial differential equations, you select that, and then you will go to another page. On the left hand side, you will see the lecture notes for various topics. There you will see the Fourier series methods or Fourier methods.
Okay, sir.
Okay. Thank you.
Thank you, sir. Have a good day.
Excuse me, sir.
Sir, guy.